1.2 Mathematical Models, a catalog of essential functions. And in this video we're just going to talk about linear functions. A mathematical model is a mathematical description, often by means of a function or an equation, of a real-world phenomenon such as the size of a population, the demand for a product, the speed of a falling object, the concentration of a product in a chemical reaction, the life expectancy of a person at birth, or the cost of emission reductions. So real-world problem, and it takes math to make the best assessment of what to do sometimes. The purpose of the model is to understand the phenomenon and perhaps, virtually always, to make predictions or inferences about future behavior. So here's kind of a diagram, schematic about the modeling process. You have some real-world problems such as those that I just described, and so you reduce it to a few, at the most, variables and formulate a mathematical model. Then you're going to apply the specifics of the what it is that you're trying to learn or understand or predict, and you solve your equation or inequality or system, whatever it is you're doing mathematically, accordingly. And then you have to interpret. You have to take the results of the math and put it into meaningful real-world terms and make predictions, and then once having done that, you're likely to go through the process again because your questions change, or you can refine what it is that you're trying to determine. A mathematical model is never a completely accurate representation of a physical situation. It is an idealization. It is a reduction of all of the real-world variables that are out there to just a few, or maybe just one. A good model simplifies reality enough to permit mathematical calculations, but is accurate enough to provide valuable conclusions. So it's got to be simple enough, and it's got to be complicated enough to be useful. It is important to realize the limitations of the model. It will never be able to account for all the contingencies of the real world. There are many different types of functions that can be used to model relationships observed in the real world. In what follows, we discuss the behavior and graphs of these functions and give examples of situations appropriately modeled by such functions. Your inferences, your predictions, are only as good as your model is reflective of the real world. But on the assumptions that it is a reflection with some accuracy, our inferences or predictions are useful. Okay, so linear models in this video, and then other models in the next video. Other models in the next video. But first, linear models. When we say that y is a linear function of x, we mean that the graph of the function is a line. Line, linear, get it? So we can use the slope-intercept form y equals mx plus b, the slope-intercept form of the equation of a line, to write a formula for the function y equals mx plus b. And slope-intercept form is also what is used by the calculator. And they use a and b, but if we use y equals mx plus b, then of course m is the slope, b is the y coordinate of the y-intercept. A characteristic feature of linear functions is that they grow at a constant rate. Okay, so growing at a constant rate. What does that mean? Well, here is f of x equals 3x minus 2. And you understand why the graph would look this way. The y-coordinate of the y-intercept is negative 2. And it's rise 3, run 1, rise 3, run 1, rise 3, run 1, because the slope is 3, which is 3 over 1, and the rise over run is 3 over 1. For every unit increase in x, there are 3 units increase in y. For every 1/10 of a unit increase in x, there are 3/10 of a unit of increase in y equals f of x, as you can see from the table. It's a constant rate of increase, so these are all the same. These are all 0.1. Okay, so constant increase in x for a linear model always results in a constant increase in y. 0.3, 0.3, 0.3 every time. If it is not the same every time, then you don't have a linear model. Notice that whenever x increases by 0.1, the value of f of x increases by 0.3. So f of x increases 3 times as fast as x. Thus, the slope of the graph y equals 3x minus 2, namely 3, can be interpreted as the rate of change of y with respect to x. That's how fast y is changing per unit change in x. And it's a constant rate, right? A constant rate. It's 0.3 every time, and so that is the constant rate, which we said is a feature of linear functions. Example: as dry air moves upward, it expands and cools. If the ground temperature is 20 degrees Celsius and the temperature at a height of 1 kilometer is 10 degrees Celsius, so it decreases when you move up, express the temperature T in degrees Celsius as a function of height h in kilometers, assuming that a linear model is appropriate. So assuming that, let's create a function, time as a function of height. The next problem is that we're going to draw a graph of the function and say, in the real world, what is the slope, which will be the coefficient of x, or the coefficient of h in this case. Whatever number is multiplied by h, what does that mean in the real world? What is the temperature at a height of 2.5? So now we're going to use the model to answer a specific question. Maybe you just happen to have a tower that's 2.5 kilometers tall. That's probably not going to happen, but who knows? Maybe your little plane flies at 2.5 kilometers up in the air. But for whatever reason, we have a need to know something about that particular real-world situation. Well, the model is going to help us determine that. Okay, so right now what we're doing is part A here. Express t as a function of height h. Okay, so express t, that's like the y, isn't it, right? Y is usually a function of x, t is a function of h. Okay. So instead of y equals mx plus b, y equals mh plus b. Now they say the problem talks about the ground. Okay, the ground temperature is 20 degrees Celsius. Well, ground, what does that mean in the mathematical model? Well, h is 0. Okay, the height is 0 on the ground. Okay, and they say when that's the case, temperature is 20. So substituting 20 for t and 0 for h, we are able to determine that b is 20. So we're going to take that 20, we're going to throw it in there for b. Now we have to get an m, and then we'll have our model. Now it'll be easier because we'll have a number in there instead of the b, and we can use other information in the problem to help us figure out the value of m. And the problem also tells us information that we haven't used yet, which is that at a height of 1 kilometer, temperature is 10 degrees Celsius. We have not used that. And we can use that along with what we've already used to find m. Okay, so y-intercept 20, and we are also given that t equals 10 when h is 1. So substituting those values, as we just said, we're going to be able to get m. M is, well, 10 is m times 1 plus 20. So we're just going to subtract 20 from both sides. Subtract 20, subtract 20, and that'll give us a value of m, which is negative 10. The slope of the line is therefore m equals negative 10, and the required linear function is t equals negative 10h plus 20. So now that we have made a function, now we're going to interpret it, and then in part C we're going to use it. So part B, draw the graph of the function in part A. What does the slope represent? Okay, so here's a graph. Here's the graph that you have when y-intercept is 20 and the slope m is negative 10, which is negative 10 over 1. So, since that is rise over run, that's what slope is, rise over run, we're going to rise negative 10 for every 1 we run. So from here, rise negative 10, run 1, rise negative 10, run 1. So we're getting these other points. And so therefore we can get the graph of the function. What does the slope represent? The slope, negative 10, well, that's going to tell us what happens with the temperature for each unit of height that we change in our elevation. So it's a rate of change of temperature with respect to height, okay, right, per rate of change of temperature with respect to height. So negative 10 per 1 kilometer change, right? As you go up, what if you go up 2.5 kilometers? It gets 10 degrees Celsius colder. Model, right? Throw 2.5 into here for h. That's what the model's about. We might not have any data at all about 2.5 kilometers. We might not have any data at all about that. but yet we want to know that. And so this model can help us do that. Maybe all of our data has to do with totally other heights. And so we just created this model and say, well, what does the model say about 2.5? Well, the model says about 2.5 that the temperature is a chilly -5 degrees Celsius. If there is no physical law or principle to help us formulate a model, as there kind of was in this last problem about temperature and height, we construct an empirical model which is based entirely on collected data. We seek a curve that fits the data in the sense that it captures the basic trend of the data points. And in this objective, it's a linear model which we hope will fit the data.